First, I'd like to thank the organizers for putting together such a wonderful and exciting meeting, and for asking me to talk here. I'm honored to be here, and it's been a great pleasure to hear all these talks. So we've heard quite a lot about Nambu's contributions to physics. There's no point in repeating them. They're characterized by deep insights, encompassing ideas from different branches of physics, kind of physics, all branches of physics, not just one particular thing. I guess these days it might be difficult to get funded by the DOE if you work in too many fields. And in particular, his work that many people talked about here about the interface between condensed matter physics and particle physics was very influential, has enormous impact. So I thought it would be nice to talk today about something else on the interface between condensed matter physics and high energy physics. And this is one of the current themes in condensed matter physics, but I'll describe it from the perspective of a high energy physicist who wanted to just understand what these people are talking about. And that turned out to be a very useful and interesting project. So this is work done in collaboration with Ed Witten, and it appeared recently on the archive. And we heard that there would be proceedings for this conference, so we thought it would really be appropriate to publish our paper in these proceedings, which will be published in this Japanese journal, Progress in Theoretical Physics. But since many of us are not condensed matter physicists, I thought just to set the stage, I'll start with the broad brush classification of phases and see how to discuss them, mostly in order to get us going. So the first broad classification of phases is gapped or gapless, or in the terminology of high energy physics, these are massless, these are massive phases, and these are characterized by correlation functions of local operators decaying like a power as we separate the operators, whereas these are characterized by the correlation functions decaying exponentially. So at very long distance, we can say that all these operators vanish because of the exponential decay. And we can further classify the phases. In the gapless case, we can have a free field theory that is characterized by simple critical exponents of free fields. And there could also be interacting theories. These are much more interesting here. The critical exponents are more complicated numbers, and there is a very rich structure with billions of papers on the subject. And in the gapped phase, there's also a subclassification. The gap theory could be trivial, or there could be a non-trivial topological field theory. So in the gap, there's either nothing there, the correlation functions of local operators are not interesting, but there could still be line operators that have non-trivial correlation functions. And this one way of thinking about them is that every such line should be thought of as the word line of a quasi-particle. So when two lines braid, that means that the quasi-particles have non-trivial statistics. So this is the further classification into trivial bulk or non-trivial bulk. And then we can further classify, even if the bulk is trivial, there could still be something interesting on the boundary. This is a further refinement. So we sit in the bulk, the local operators all vanish, all the line operators have trivial correlation functions. So if we just sit in the bulk, we have no idea that something interesting is happening. But if we have a boundary, there could be all sorts of things on the boundary. First, the boundary could be trivial. There could be gapless, massless boundary modes, or there could be a gap topological field theory on the boundary. So in this case, there's nothing interesting. In this case, there are some massless particles, or a field theory, a massless field theory, or a conformal field theory on the boundary. That's what happens here. And in this case, correlation functions decay exponentially, but they are non-trivial lines and non-trivial correlation functions, some non-trivial long-range order. And in the case when the bulk has a topological field theory, we still have this further classification into all these cases. And in these cases, in these two cases, where the bulk is trivial, and on the boundary we have either massless modes or a topological field theory, say that the gap, the bulk, is not completely trivial. Even though when we sit in the bulk, we don't see that there's something interesting, the fact that on the boundary there's something non-trivial tells us that there's something non-trivial already in the bulk that gives rise to these excitations on the boundary. So that comes under the name of SPT phase. So continuing at the same rate of lightning review, let me say a few words about the topological insulators. And the first thing, what's an insulator for a high-energy physicist? An insulator is a system that has a global U1 symmetry that is not broken. So the unbroken global U1, I denote with big A. This would be the electromagnetic vector potential. It's electromagnetic gauge field. And as emphasized earlier today, we'll think of it as a classical gauge field. We are not going to consider the fluctuations of big A. Big A is a frozen background. But we will contemplate non-trivial backgrounds. So we can have, say, a magnetic monopole. Even though there are no magnetic monopoles in nature, it's useful to think what would happen if we couple the system to the classical background field of a magnetic monopole. And further, we have a gapped and trivial bulk. So this is our starting point. We have a system with a U1 symmetry, and it has a gapped and trivial bulk. The bulk observer doesn't see anything interesting. And furthermore, we are going to assume that the system is time reversal invariant. Pragmatically, we don't put any magnetic field or anything like that. If the system is relativistic, we usually see parity invariant, but we should be a little bit more careful. So I'll call it time reversal invariant. If you're thinking of it as a Euclidean field theory, you're not making a terrible mistake by saying that it's parity invariant. And in this case of the topological insulator, the reason it is interesting is that even though the bulk is boring, there could still be something interesting on the boundary. So people studied various examples. In the simplest example, there are massless fermions on the boundary. So we have nothing in the bulk. It's insulating, but there are massless fermions, massless charge fermions on the boundary. And that is the simplest example. And then various people contemplated possibilities and constructed examples where these fermions can be lifted and having a gapped state, but still a topological field theory on the boundary. So let's give a simple example that demonstrates how this thing works. Consider this system, and for simplicity, I'll assume the system is relativistic just because it's easier for me to think about it. That's not essential for what I'm saying. Everything can be done without assuming relativity. So assuming a system of a free electron coupled under electromagnetism, and it has charge plus m in the vacuum outside, and it has mass m positive in the vacuum, and it has mass minus m in the interior. Since the mass is real everywhere, the system is time reversal invariant. This is common. We have seen things like that in high energy physics, in domain walls, in fields in extra dimensions, and so forth, and this is the condensed matter version of the same problem. So the mass is positive outside, and it's negative inside. And as I said, since the mass is real, it preserves both electromagnetism, this global U1 symmetry, and time reversal. And in this case, it also preserves charge conjugation, but that's not essential to our problem because that's not a symmetry in condensed matter physics, except in special situations like the one discussed by Son this morning. And as the mass varies in space, it's plus m outside, and then it goes to 0 along the boundary, and then it continues at minus m. At some point, it has to be 0, and therefore, there are massless fermions on the boundary. This was first discovered by Jacques and Rebbe when they just solved the Dirac equation of this setup. So this is a simple way of understanding why we have massless fermions on the boundary. There's another way of understanding it by performing a chiral rotation. Let's take the system in the bulk and perform a chiral rotation on the fermion. That has the effect of flipping the sign of the mass. If we do that, the mass is positive everywhere. The mass is positive both inside and outside. But instead of the mass changing sign, we have an induced term inside, 1 over 8 pi, and I'm very, very careful with the 8 pi. I could have had a typo in the slides, but in the paper we tried to be careful because the whole story is about the 2's and the proper normalization here, so we should really be careful about that. So we have a term like that. The first term is theta of electromagnetism, which is pi inside and 0 outside. There's also a gravitational anomaly, a term which is absolutely crucial to get the physics straight, but in most of the talk I'm going to ignore it. but in a deeper understanding, we have to pay attention to it. So instead of thinking of a mass that changes sign, we say the mass is always positive, but instead we have electromagnetism with theta being pi inside and 0 outside, and as we know, this is time reversal invariant and clearly U1 invariant. So this is our starting point. I want to give another perspective on these boundary modes. So the theory on the boundary is a 2 plus 1 dimensional theory, which has complex massless fermions on the boundary. And this system preserves U1A, the global U1 symmetry that we can rotate it by a phase, and it has time reversal symmetry. This system is known to have what is called parity anomaly. And the statement of parity anomaly is that this system has both U1A and T naively, but it's hard to preserve both of them. Something has to be sacrificed. And that's common with anomalies. We have various requirements. We would like to satisfy all of them, but one of them has to be sacrificed. And there are different presentations where we sacrifice different things. So the canonical, old-fashioned way of doing it is we preserve either U1A or time reversal, and the choice that everybody prefers is to preserve the U1 symmetry, because that's what couples to electromagnetism, and say that this system is not parity invariant because of the parity anomaly, or it's not time reversal. Despite being classically time reversal, it's really not time reversal invariant. But there's a third option, which is always the case, where you have to sacrifice something, that you sacrifice one of these assumptions that you did not even spell out, an assumption that this system has. And that is the statement that you can preserve both U1A and T, but the system is not going to be 2 plus 1 dimensional. So the system is really going to be 3 plus 1 dimensional. It is attached to a bulk. There is theta equals pi in that bulk that we talked about. And this is an example. So in this case, we have both symmetries, but we need the bulk. And this is an example of what in high energy physics called the anomaly inflow situation, first discovered by Cullen and Harvey, except that Cullen and Harvey had an ordinary anomaly, and an ordinary anomaly flows, and it is saturated by massless modes on the boundary. And the anomaly here is more subtle. This is only a Z2 anomaly. This is this parity anomaly. So one has to be a little bit more careful. But conceptually, it's the same phenomenon as the anomaly inflow of Cullen and Harvey. So now we understand why we have U1, why we have these massless modes. There's a symmetry reason underlying it. It's not because we did a complicated dynamical computation that gave us the massless mode. There's a symmetry in the problem, and there's an anomaly. These are robust things. So if we take this system and we perturb it a little bit while preserving the symmetries, the fermions are going to stay there. So that's absolutely crucial. Alternatively, we can just start with this theta equals pi inside, but not outside. And we say, okay, as I've already said, small perturbations are not going to change the system. We can change the parameters a little bit and paint the material from outside with some other material. Small changes are not going to affect the answer, but we could ask, are there big changes that can change it? Can we make a large perturbation and gap the system? So it's not going to be nearby in field space, it has to be very far, but can we do that? Is there a way of doing it? Something will have to remain on the boundary because we motivated these fermions by saying that there's an anomaly inflow. So something should still be on the boundary, something non-trivial, to soak this anomaly. But if it is gapped, this must be a topological field theory. That's actually a very interesting question. Can there be a topological field theory there? And the reason this is interesting is that if somebody hands me a topological field theory and asks, can that be the boundary state? I don't even know how to answer this question. The system has to have time reversal symmetry, must have a U1 symmetry. That we can check. But what's non-trivial is that it should have the right anomaly. And that anomaly, checking that it has the right anomaly, is very, very difficult, and it's still a very interesting open problem, how to characterize the anomaly completely and to make sure that the topological field theory has the right anomaly, and that's why it should be there. And it's really important that I motivate everything by the anomaly because that's robust. Does not depend on the details of the Hamiltonian. It's only the symmetries and the anomaly. So this is an open question, and it's particularly challenging because of the gravitational anomalies. The ordinary U1 anomaly, this F wedge F, that's relatively easy to check, but the gravitational anomaly is more challenging. So let me give a caricature of what we're doing here, and it's really very similar to Son's talk this morning. Son said at a short distance, we have what he called the theory of everything. This is Hamiltonian of electrons with some Coulomb interaction, some kinetic term, and it's very complicated. There could be all sorts of other things. And then at long distance, there's a macroscopic system, which he referred to as the standard model. I hope I got the terminology straight. So, and usually the challenge in condensed matter physics is to start here from this theory of everything and to flow and find the correct long-distance behavior. Given a theory at short distance, what's the answer at long distance? And what is often being done is the following. We consider a simplified model, which should not be viewed as an exact description of nature. This is some kind of a caricature of nature. It's not the system we are interested in. But this model is interesting because, first of all, it flows to the same macroscopic theory. The macroscopic theory is exact. This is exact and complicated, and this is some kind of a broad brush description which is not accurate. But it does capture some of the physics correctly. It flows correctly to the infrared, to long distance, to find the long distance physics, and it also has some collective excitations, various quasi-particles, and it captures the quasi-particles correctly, their quantum numbers, their statistics, but it might not describe correctly their masses and all their interactions. For that, we really need the more complicated system. But this is particularly interesting, this simplified model, if it's weakly coupled. And it's really besides the point to guess such a simplified model, a model that describes the physics and which we will analyze and flow to long distance, if this model is itself strongly coupled. So this I really emphasize that this model is particularly useful when it's weakly coupled, when we don't need any guesswork for what it does. We don't need any dynamical assumption about what it does, because here we calculate. So the purpose of this talk is to do exactly that, to find such a simplified model, and I underscore the fact that everything will be done at weak coupling. The fact that everything will be done at weak coupling would mean that we really know what we're doing, everything is under control, and conversely, we have no room to hide. We cannot say, well, there will be some strong coupling effect that we do not understand that will fix things, because everything will be at weak coupling. So let me say a few more words about these models. I said that the macroscopic model gives an exact description. I've already said that. The simplified model flows to it. It's not exact. Semi-classical methods are going to be reliable, so we know what we're doing. And I would also like to emphasize that there's a technique which is common in high-energy physics using a 't Hooft anomaly matching conditions, which allows us to control what happens at short distance versus long distance, especially when we have some kind of strong coupling phenomenon. So from the microscopic model, we go to long distance using perhaps strong coupling. Here, we're going to have two other models, the simplified model and the long distance model, but we would like to make sure that they have the same symmetries. That's not a big deal. That's obvious to everybody, but the non-trivial insight of a 't Hooft in the late 70s that we should also go after the anomalies, and the anomalies should also match. And that gives a very powerful tool, especially in a situation like here, where everything is driven by the anomaly. So what we'll do is present you a simplified model for the topological insulator, and I'm going to pull particles out of a hat. Doesn't matter what it is. I'll describe a model, and then we'll just analyze it. So we're going to start with the same model with a single fermion on the boundary, this massless charge fermion on the boundary, and we're going to throw in a few more particles. So we're going to say that there is an emergent U1A gauge field, and I emphasize this is U1, it's compact, it lives only on the boundary. This is a 2 + 1 dimensional field, and this, unlike big A, little a is a dynamical field. It fluctuates. Big A is a classical background field. So that's the first thing we do. And we also add a scalar field W, which has charge 1 under that symmetry. And the purpose of this field is to allow us to Higgs the U1A. So something I learned from Steve Schenker, although he might not be the first to say that, is a situation like that, where we have a field of charge 1 Higgsing the U1 symmetry. It is as if we haven't done anything. We added a U1 gauge field and a field that Higgses it. So we are really going to be in the Higgs phase of that U1A. And we're also going to have fermions, chi, which have some charges under these two symmetries. So, and I'll motivate, so it looks like we have a laundry list of particles, but I'll motivate what every one of them is doing, so it will not look so random. So the charges for chi carries charge 1 under this, and charge 2s under u1 little a, and s has to be an integer. So it carries charge 1 under u1a, so it suffers from the parity anomaly, or the time reversal anomaly, under u1 big A, but there is no separate time reversal anomaly with u1 little a, because the charge under u1 little a is even. And that has already figured in Son's talk this morning, so chi carries even charge under that. Below, we'll also argue that this S has to be even, but that's for more subtle reasons. Now, well, this will come out. Well, I don't need to impose it, I need to check that there is a set, and there will be an electron coming out of that. So let's first start with this phase, with W is non-zero. This is the phase I alluded to before. When W is non-zero, this guy is gone. It just Higgsed. It doesn't even leave an unbroken discrete subgroup because this is the basic charge. And so this is gone, and this is gone, and we are left only with chi with charge 1. This is precisely the system we started with. That's great. We have a system whose only massless modes are fermions with charge 1 under U1 big A, and therefore we know that this system has the right anomaly. We don't know how to compute the anomaly, but we know that this system has the right anomaly because it's the same system we started with, namely these massless fermions on the boundary. Now we're going to start changing phases in this system and keeping track of what goes up and what goes down in the spectrum, but the anomaly is going to remain the same. And I emphasize that we'll change parameters, we'll go very far in field space, but h bar will be constantly small, consistently small. So whatever we do, whatever particles we see, we'll be able to see that semi-classically. There will be no surprises of some collective excitation that we don't understand. It will all be with the things you can see with the naked eye. So I've already emphasized that this system contains the previous one, and therefore it has the same anomaly, including the same gravitational anomalies. So now we're going to throw in another scalar field whose sole purpose is to lift the fermions, because that's what we would like to do. We would like to see whether we can gap the fermions and give them a mass. So we just add phi, which couples to two chi's, and the charges of phi are just read off from the fact that this thing should be gauge invariant. So it has chi has charge 1, 2s, so phi has charge 2, 4s, and we add such a term to the Lagrangian. In the previous phase, phi was massive, and since phi was massive, this made no difference. Now we're going to go to a phase where phi gets an expectation value, and then we'll get something interesting. So now we go to this phase, W is 0, but phi has an expectation value, and I claim that the theory is gapped. Let's check that. As I said, everything is weakly coupled, so we should be able to see it with the naked eye. The U1 asymmetry, the gauge symmetry, this emergent gauge symmetry that we added, is Higgs down to a discrete subgroup, Z4s. And there are no massless gauge fields. Chi acquires a mass, so the photon, or the gauge field for U1 little a, gets a mass. Chi acquires a mass from this coupling, and therefore the spectrum is completely massive. And I emphasize that time reversal in the U1 asymmetry remain unbroken, because that was the name of the game. Try to gap the system while preserving both U1a and time reversal. That was the goal, and we achieved that at weak coupling. So we don't need to assume that there's some complicated vortex that condenses or this and that. It's all done in the Lagrangian, semi-classically. So what have we established? Our system has the right anomaly to be a boundary state. That was by checking in the first phase. And in this phase, we found that it has a gap boundary phase with a topological field theory. And again, I underscore the fact that everything can be analyzed explicitly. Let's work out the massive spectrum. That's interesting because, first of all, we can calculate it. So whatever we can calculate is interesting. We should do it. But second, in the condensed matter language, these are the quasi-particles. And we might not trust their masses or their precise properties, but their quantum numbers are trustable. So we just take the Lagrangian we have, We go to the vacuum with non-zero expectation value for phi. We expand everything around it, and we read off the spectrum. So first we have W quanta. These are particles which are neutral under this U1 big A and carry charge 1 under the discrete gauge symmetry. So that's good to have. We also have chi quanta. They are neutral under U1A, and they transform also under the discrete symmetry. Don't try to follow the algebra, because it might be difficult to do it in your head unless you're experienced with that. But I really emphasize that this is something you read off from the Lagrangian. There's nothing mysterious here. Here comes something a little bit more interesting. We had U1, which was Higgs down to a discrete subgroup, Z4S. And therefore, we have interesting vortices, very much like the vortices of, say, the superconductor. Except that here, these are vortices of the emergent gauge field, U1A. So we know what these are. They have different names associated with these vortices, depending on which field you come from. And these vortices are particularly interesting because if you work out the fermion zero modes on them, you realize that the single vortex, which has V equals 1, has an odd number of fermion zero modes. Odd number of fermion zero, this is something you find classically. You just solve the Dirac equation in the background of the vortex. Odd number of fermion zero mode means that in 4 dimensions, this is a string, in 3 plus 1. In 2 plus 1 dimensions, this is a particle. So there is going to be a particle with non-abelian statistics. This is the signature of non-abelian statistics. The signature is odd number of fermion zero modes. So we have this object, and that's true for all odd V vortices, but the even guys have abelian statistics. The spectrum also has monopole operators that are interesting. So every 2 plus 1 dimensional theory that has a U1 gauge symmetry has a global U1 symmetry. By calculating. Yeah, well, there's an even fermion number. Yeah, you can actually. There could have been, but it's not. That's the nice thing of a weakly coupled model, that every question has an answer. Right, because you just calculate it. I'll later give another perspective of the whole thing, and then it will become completely obvious to you. So every 2 plus 1 dimensional system that has a U1 emergent U1 gauge field has a global conserved current, whose the current is essentially dA, the field strength of that U1. But our microscopic theory, so what is this current? This is a global symmetry, and the charged objects are monopole operators. This is a monopole of that emergent U1. This is a local operator. It is constructed non-locally, but it is a local operator in the sense that it has local correlation functions. And it is charged under the symmetry. But the original theory of everything that, as Sand described it, or the original system of electrons did not have that symmetry. So we have to add this operator to the Lagrangian. This does not invalidate anything we said because we can add it with a small coefficient. The sole purpose is to explicitly break that symmetry. So the microscopic system does not have that symmetry, so we would like to add it to the Hamiltonian. And again, I emphasize this can all be done at weak coupling. We keep h bar small, coefficient small, everything is still easy. So we have to add this operator to the Hamiltonian, but here we find a surprise, something that we did not expect. If you work out the quantum numbers of this monopole, which is again something you just calculate with semi-classical quantization, you realize that this monopole operator has all sorts of operators with various U1A charges and U1 little a charges and various spins. But if you want to add it to the Hamiltonian, it should be invariant under U1 big A and U1 little a, and it has spin which can be half integer. So this monopole operator that we tried to add to the Hamiltonian turns out that, depending on the parameters, might have integer or half integer spin. This is not obvious, but it comes from the computation. I will later give another perspective of that. So therefore, we can add it to the Hamiltonian only when S is even. So the first reaction is let's make S even so that we can really play the game, but soon we'll like to understand better why this thing happened. So earlier I had the comment that S should better be even, and now I explain why. And I claim that this is really a symptom of a much more general phenomenon. There's a much more general phenomena that we need to worry about, and this is just a sign of it. So we call it the spin-charge relation. So consider a system of electrons, like the Hamiltonian that Son wrote this morning. There are some electrons, they interact, and they couple to each other with Coulomb force, and they have kinetic terms, and this and that. So as long as the nuclear spins are not important, there is a selection rule in the spectrum. All the states of the system in finite volume and all the local operators satisfy this selection rule. That every local operator in condensed matter system like that, subject to these conditions that I spell out, twice the spin is the U1 charge mod 2. Namely, the electron has spin 1/2 and odd charge. 2 electrons have integer spin and even charge. So this is a selection rule that should be satisfied for all the excitations in the spectrum. And this turns out to be a powerful constraint. This is very much like a 't Hooft. There's a subtle thing that has to be true, and it's true at short distance. It must be true at long distance. So we could track it through the flow and make sure that our answer in the end of the day satisfies this selection rule. And the same should be true for our simplified model. So there are various ways of thinking about it. I'll present here something which is slightly more technical. So if you don't follow the more technical explanation, just decouple for a slide or two, but make sure that you come back afterwards. So what does a 't Hooft say? A 't Hooft said that when we have a system that has a global symmetry, it's convenient to couple it to a background gauge field. The purpose of the gauge field is not that we really couple it to it, but this is a device to keep track of various anomalies. That's what a 't Hooft told us. And similarly, we would like to couple our system to background metric and background A. We've already coupled it to background A, and I alluded to the background metric. And again, we're not interested in the condensed matter system in curved space. We don't really care about that, but this is a device that allows us to control the behavior, the infrared behavior. It's not that we should couple it to curved space, it's the fact that we can couple it to curved space to give us information. So naively, we have spinners, so the background manifold, the background metric, should have a spin structure. We have spinners, which must have a spin structure. But actually, we can do a little better than that. We can turn big A to be a spin C connection. Let me say what it is. A spin C connection means that U1A gauge field, A is not really a U1 gauge field. It can have half-integer fluxes, provided they are correlated with the obstruction to spin structure. If you didn't follow that, don't worry. And this is the comment that I said before. We are not really interested in the behavior of our system in curved space. This is just a tool, a device to control the long-distance physics. So the upshot of all that is that the macroscopic theory should also satisfy this selection rule. We started from a system of electrons. The fact that we could couple it in this way means that the macroscopic answer we should also be able to couple it in that way, and therefore this selection rule should be satisfied. So now let's go back to our Lagrangian. So we had W and chi and phi, and they had various quantum numbers and so forth. The details I emphasize again are not important. But the key thing is that all the perturbative excitations satisfy the spin-charge relation, and you can easily check that. For example, you can make something with the quantum numbers of the electron to answer your question, and it satisfies this spin-charge relation. So for example, this is a scalar which has even charge. This is a fermion, it has odd charge. This is a scalar, it has even charge. So all the perturbative excitations satisfy this selection rule, but the monopole operators do not. This is again the sign of an anomaly. There is something that the perturbative excitations satisfy, but the non-perturbative excitations don't. So this is a new selection rule, and in this case we see that the selection rule is violated by a new kind of anomaly. So I've already said that this is an anomaly, so we must exclude these models. Now, if you decouple, this is the time to wake up, I'll very briefly describe how a low-energy observer describes all that. Because we had a microscopic, we had the full microscopic model, the complicated one, and then we had this simplified model, the simplified model that flows to it, but we also have the low-energy observer, and now we should be able to compute what the low-energy observer sees. Because the low-energy observer we thought everything was weakly coupled, so we'd just be able to integrate out the massive modes and construct a topological field theory at long distance, topological field theory that has all the desired properties. So first, let's describe the discrete gauge theory. So the discrete gauge theory, the Z4S gauge theory, can be described as a U1 times U1 Chern-Simons term. This coupling appeared already in Subir's talk this morning. He said he had difficulties with our paper. So now I'll give you the two-line summary of what you need from that paper. A was originally there. This is the U1 that was Higgs to the discrete symmetry. And it was Higgs by an expectation value of phi. The phase of phi, would be the Nambu-Goldstone boson if the symmetry had been a global symmetry, but this is the mode that is being eaten. It's a compact scalar in 2+1 dimensions. It can be dualized to a U1 gauge field whose name in this slide is C. Another way of saying it is that C appears linearly in this Lagrangian. So the equation of motion of C constrains A to be a Z4H gauge field. So these two presentations are the same. And the coupling to big A follows from the coupling of phi. So you can actually do the duality of the phase of phi and construct this Lagrangian. So this is one thing we should have at long distance. We definitely have a discrete gauge symmetry, and this is a presentation of that discrete gauge symmetry. We can also integrate out the fermions, and I'll first do it carelessly. The careless way of doing it is that when we integrate out fermions, we get level 1/2 Chern-Simons term. This is careless because actually we should really follow Alvarez, Gomez, De La Petra, and Moore, who said this is the eta invariant. So recall that I'm making a mistake. I'll later fix it. But before, let's just follow this presentation. So we get 1/8 pi, which means k equals 1/2, times the gauge fields that the fermions couple to. So let's collect all the terms. This thing tells us that we have a Z4S gauge theory. And this comes from integrating out the fermions. So now we can open the parentheses. The term with little a from here and little a from here is what is known as a Dirac-Witten term in the discrete gauge theory. The advantage of this presentation is that instead of thinking of the complicated group cohomology, some people like it, some people don't, this is easier. You just write down the Lagrangian. This is just a diagonal Chern-Simons term for little a. This is the Dirac-Witten term. We also have various couplings of little a to big A, but the only term here which is not properly normalized is this big A with a coefficient 1/8 pi. So this is the wrong coefficient. It's 1/2. Everything else has a multiple of 1/4 pi or 1/2 pi. This has 1/8 pi. This is the wrong coefficient, and that reflects the anomaly. This is a sign that our system has the right anomaly under big A to be the boundary state. We knew this had to work, but this is a consistency check of our analysis. It had to work because of this line of reasoning that we had a phase with the right spectrum, etc., etc. And the nice thing about this Lagrangian is that it's free. So this is a free Chern-Simons theory. It's an abelian Chern-Simons theory. It's completely straightforward to analyze it, to write all the lines and their correlation functions. And that looks like a good answer to be for what the topological field theory should be. For example, the Wilson line of little a describes the world line of a quasi-particle. This was this thing we called W before. So that looks like a nice answer, except that this cannot be right. It cannot be right because we have made a number of mistakes. So let me enumerate the mistakes. So this is the abelian Lagrangian that we study. And this cannot be the whole story because this is the list of mistakes. First of all, we don't have a line operator associated with the chi quasi-particle, this fermion. Second, this system is not T invariant. Third, this line of the gauge field C should represent the vortices. This is something that little a has a Aharonov-Bohm phase as we go around it. It describes the vortices. But I emphasized before that the vortices should have non-abelian statistics, whereas this system is abelian, so everything has abelian statistics. So that's also wrong. And finally, chi, we integrated out incorrectly. We said that it's a Chern-Simons term, but in fact, we should use the eta invariant. So this is the list of mistakes. It looks quite awful, but this cannot be totally wrong because we sort of had a derivation of it. So it means that we should be able to fix it. So I'll do it briefly here. So it turns out that there's a simple fix that fixes all these problems. There's a 2 plus 1 dimensional topological field theory, which is the counterpart of Ising. Another way of saying it, every 3-dimensional topological field theory, and the 2 plus 1 dimensional topological field theory, has a corresponding 1 plus 1 theory on the boundary. And the simplest non-abelian 1 plus 1 dimensional theory on the boundary is the Ising model. It has 3 fields, the identity with spin 0, the fermion with spin 1/2, and the spin field with spin 1/16, and the non-abelian statistics is in this W of sigma. And if this is a rational conformal field theory on the boundary, there is a corresponding bulk 2 plus 1 dimensional topological field theory associated with it. So I'm not even going to describe it here. I'll just say that there is such a theory. It can be given a very explicit description. And now we're going to take the two sectors, quotient them by Z2, and this is the total answer. So in the end of the day, the lines are whatever we had from the abelian sector times what we had from the non-abelian sector with some selection rule depending on whether V is even or odd, motivated by the discussion we had of the vortices, which one is abelian and which one is non-abelian. And with this thing, we have complete match between the topological field theory and the semi-classical picture of the quasi-particles. So we had this picture of the quasi-particles. Some of them were visible at the level of the Lagrangians. These are excitations in the Lagrangians. Others were vortices that had to be analyzed more carefully because of the fermion zero modes. This system gives one-to-one match. It gives the same spins, the same statistics, and so forth. And it even has the same anomaly in the spin-charge relation. So everything can be reproduced in this language. So the integers are n here. This is the number of W quanta. V is the vorticity, and this thing W psi, if we put 0 here and here, this is the fundamental chi quanta. So the spin statistics and the charges of these lines reproduce the semi-classical results. This satisfies the spin-charge relation that I mentioned before, and it exhibits the same anomaly. It forces S to be even, and for the simplest case, S equals 2, this topological field theory appeared in this paper, although without a weakly coupled derivation like ours. So let me conclude. How am I doing with time? I have 7 minutes, according to my clock, because I was told 50 plus 10. I'm happy to talk forever. So in conclusion, if you fell asleep now, you can really wake up. The end is in sight. Topological phases of matter are interesting. I find this subject fascinating. I'm really happy with the interaction between high-energy physicists and condensed matter physicists. There's another way of thinking about things which is, I think, useful for both sides. Some of these things have already been encountered by high-energy physicists, but most of them are really new and interesting. And it combines many different things. There is interesting mathematics, the study of these anomalies, interesting quantum field theory, condensed matter physics, maybe agrees even with experiment, and there might even be technological applications. Who knows what else can come here? So that's a good thing to do. What did we do? We presented a weakly couple system, and I underscore the weakly couple, which is T invariant and the global U1 symmetry, so that it has the right symmetries. And it has a phase which has massless fermions and nothing else, and therefore it has the right anomaly. It could be a boundary state. And it has another phase which is gapped, and it's a total topological quantum field theory. So the same system exhibits these two phases. It means it has the right anomaly, and everything is calculable here. And it's explicit. So I don't need to assume any dynamics that is not explicit. Even though the analysis is weakly coupled, and Greg asked me a question, I say you just calculate it, it turns out to be quite subtle. And it's full of interesting subtleties, a bit subtleties at weakly coupled field theory, odd number of fermion zero modes, the spin-charge relation, the anomaly in spin-charge relation. So there are all sorts of new things that maybe other people knew, but were new to me. I did not know that such things.
You have the Ising TQFT by hand, right?
These can actually be derived. In the paper, we actually derived the Ising CFT. It comes from the fact that you have to use the eta invariant rather than the partition function of the Lagrangian of that Ising can be taken to be can be taken to be the eta of this gauge field. That's one answer. The other answer is just look at the quasi-particles and ask, what has these quantum numbers? Because semi-classically, you compute the spin of the vortices. You compute how they transform under the unbroken Z4S gauge symmetry. All these things are computable. You can compute the braiding matrices. But you can do everything using the semi-classical description of the microscopic Lagrangian. You don't need the topological field theory. The topological field theory, in the end, is a way of summarizing that information. Right? So everything can be calculated microscopically, but you can even get this Ising sector. So I showed these new consistency conditions. So the spin-charge relation appeared before. It appears not quite in this language in the paper of Belov and Moore, and perhaps even earlier than that. This is as far as I could track it down, but perhaps it appears even earlier, so no claim here. But this use of it, I think, is new. There are new anomalies. The anomaly in this spin-charge relation, something that you write a Lagrangian that naively satisfies the spin-charge relation, but in fact it does not. We found many more models. I presented one model here, but it's easy to generalize that. Add more fermions with different charges, more scalars with different charges, more gauge fields. You can write something much more complicated. All you need to make sure is that it has a phase with just fermions, and everything else is gapped. That gives you some consistency conditions of the charges. And then look for other phases that are gapped. So, and once you get used to it, it really goes very fast. So you can construct many other topological field theories that could do the job. To some extent, we generalize that to the topological superconductor, this is where the U1A is really replaced by Z2. So you should replace the whole thing, and you can tell the whole story again for the topological superconductor. Here, the analysis is not as complete as for the topological insulator, but we reproduce many of the results in the literature in this language and many others. And we also have some puzzles with regard to the literature. And what's more interesting is that there are many, many questions that one can think about that we didn't answer. So I'd like to end the talk with this photo. This was Toru Iguchi's 60th birthday in Kyoto. I met Nambu there. We really had a wonderful time, and I met him before, but when we met here in Kyoto, we spent a lot of time together, and it was really a lot of fun. What a wonderful person, and it made me very happy. And this photo also has something else which is nice about it. It introduces the next speaker. So thank you.
Well, I think it's a very simple question. So I thought you started with the two-dimensional space as a boundary of the bulk, but then at the end of the day, you also had a boundary to this two-dimensional space and introduced 1 + 1 dimensional CFT. So where is that boundary?
Okay, I introduced that only to describe the 2 + 1 dimensional field theory. So put aside whatever we said before. Now we study 2 + 1 dimensional field theories. They could have a boundary, and one way of characterizing the 2 + 1 dimensional topological field theory is by saying what it has on its boundary. Now, you don't have to do that, and there are other ways of characterizing the 2 + 1 dimensional field theory, for example, using the braiding and fusion matrices, or by writing down the Lagrangian. So there are various ways of doing it. So for this particular system, there are various ways of doing it. We can write its Lagrangian, as I said, it's the eta invariant, or we could describe it as a coset SU2 times U1 and write it as a Lagrangian for a U2 gauge field, or we can describe it using the braiding and fusion of the Ising system. These are just different presentations of the same field theory. I wanted to connect to things that some people in the audience know. Other people might prefer another presentation of the same theory, but it makes no difference. This is the theory. This is a theory which has 3 lines, and it has to be coupled in that particular way. Did I answer your question?
Yeah, I have two small questions. So one was with the spin-charge relation. I'm not sure I fully understood. When you were talking about spin, were you assuming rotational symmetry?
Yep.
So if we just have a system with just time reversal, presumably you want to replace spin with some concept of Kramers degeneracy or something like that?
Well, that's
In a more general
subtle.
context.
That's more subtle. The spin still makes sense. We can rotate the system and ask what's the spin of the particle. Then, because of time reversal symmetry, it might or might not be doubled because of Kramer doubling. But that's this is a secondary question. First, let's match the spin. Every particle should have a spin. So this is a statement about the spins of the particles.
But if we don't have rotational symmetry, I guess I'm saying presumably you still want to have some matching.
If you don't have rotational symmetry, there might be a weaker statement. There might be a weaker statement that would still lead to a consistency condition. But I suspect that by the time you are at long distances and you have this long distance physics, then you're in the continuum. You must have full rotation invariance. And for that, you should be able to define the spins of the particles. One wanted to comment on this? I think that's what he said. But I do not know whether this would be as powerful as this 2-pi rotation. But I can say it differently. Imagine you have a system on the lattice. So that's good. Now we can embed the lattice in this spin C manifold. I could do that. It's not, again, this is not something I'm interested in, and I barely know what a spin C manifold is, but I can take the same lattice Hamiltonian and put it in this spin C manifold, and it's consistent. So the electrons that hop around are still have this property. So whatever it is, it should also be true at long distance. And in the topological field theory, there's a simple way of saying whether the spin-charge relation is satisfied or not. You just look at the spins of the lines. There's a formula for the spins of the line. It's basically a relation that I think appeared for the first time in Belov and Moore between the diagonal matrix elements of K and the charge of these particles. One of them is mod 2, the other, or something like that. Well, for me, there's only one. There's one number per line, and the lines that can appear, it's a statement of the spin of the system on closed space. So it's not every single line. It's only those lines that can exist in compact space. So there are lines that can appear in constant space. They have spin which is either even half integer or integer, no fractions there, and their charge is integer, and it's either odd or even. And there's a selection rule, so the odd guys come with half integer spin. So for example, the fractional quantum Hall effect, the 1/3, satisfies this relation. But the thing is that such consistency conditions, which are common, is 't Hooft anomaly matching. In physics, there's some consistency conditions on the long distance physics. If you have a system and you landed on the right answer, it doesn't teach you anything. But it's very good to know because you might have landed on the wrong answer, and that's a way of weeding out the wrong answers.
You have a weakly coupled system that can give you Dycroft-Witten theory for non-abelian group?
No. Do you want a more detailed answer? Before even the Dycroft-Witten theory, you just ask whether you can just describe the pure gauge theory in terms of abelian gauge fields. And forget what Dycroft and Witten added was the extra term. The topological field theory, just a gauge theory whose gauge group is the dihedral group. That existed before Dycroft and Witten. What they said is that in this topological field theory, you can add an extra term. I don't even know how to answer the first question for the dihedral group. For Zn, for abelian groups, we can write this Lagrangian that appeared in your paper for the kinetic, the group itself, and you can add a natural term, which is the Dycroft-Witten term. Subir had a question?
So what role? You didn't discuss the gravitational anomaly very much.
Right.
So
constraints?
Yes, absolutely. So first of all, you can construct other models that are almost as good, except that the gravitational anomaly is not right, which shows, so they cannot be really boundary states of a topological insulator. That's just to show that satisfying there's another consistency condition that the R wedge R has to be with the right coefficient. That's the first thing. But there are more subtle gravitational anomalies that I didn't even discuss here, those that give you the periodicity of the topological superconductor. They can also be described as various gravitational anomalies. Some of them are more subtle, that you need non-orientable manifolds and so forth. This is a much more subtle system. I don't think there is a complete understanding of that. I certainly don't have a complete understanding. But that's what, in the end, controls this periodicity of the topological superconductor, this mod 8 or mod 16 of the topological superconductor. In this system, you can actually, when you can do it, when you follow our route, you see that it's consistent with the understanding there. So there are two ways of thinking about it. One, you start from something that clearly satisfies the right consistency conditions, and you start adding stuff to gap it, and then you land on an answer. I think a better one would be a complete characterization of the anomaly, and then saying, we want a system that has this anomaly, and this is how we check. That would be a complete answer. And I think it's more conceptual than having a system with a layer of this and a layer of that, and then you couple and this and that, and you put it near something, and you unhiggs and higgs and so forth. Because it's all controlled by a small number of integers which control these anomalies, and it's all driven by that anomaly.